What if you could see the invisible flow of electricity? How would you detect the faintest whisper of current, or precisely measure its strength? For centuries, one ingenious device has been the cornerstone of electrical measurement, revealing the hidden dynamics of circuits: the galvanometer. It's more than just a meter, it's a fundamental principle brought to life. At its core, a galvanometer is an electromechanical instrument designed to detect and measure small electric currents. It operates on the principle that a current-carrying coil placed in a magnetic field experiences a torque. This torque causes the coil to deflect, and the extent of this deflection is directly proportional to the current flowing through it. This elegant device transformed our understanding of electricity. Before its invention, detecting current was a crude affair. The galvanometer provided a sensitive, quantitative means to observe and analyze electrical phenomena, paving the way for countless discoveries and technological advancements. The operational principle of a galvanometer is rooted in the Lorentz force. When an electric current flows through a conductor, and that conductor is situated within a magnetic field, it experiences a force. In a galvanometer, this force acts on the sides of a current-carrying coil. These forces produce a turning effect, or torque, on the coil. The torque is proportional to the current, the strength of the magnetic field, the number of turns in the coil, and its area. This rotational motion is then translated into a visible deflection, typically by a pointer moving across a calibrated scale. A typical moving coil galvanometer, often called a D'Arsonval or Weston type, comprises several key components. A light rectangular coil, usually wound with fine insulated copper wire, is the heart of the device. This coil is suspended within the strong magnetic field of a permanent magnet. The suspension system is crucial. It often involves a delicate phosphor-bronze strip that also serves as one of the current leads. This strip provides the restoring torque, pulling the coil back to its zero position when no current flows. A soft iron core is often placed inside the coil to concentrate the magnetic field lines, enhancing sensitivity. While the moving coil galvanometer is most common, several types exist, each suited for specific applications. The tangent galvanometer, an older design, uses the Earth's magnetic field and a tangent law to measure current. It's primarily a historical and educational tool today. The ballistic galvanometer is designed to measure the total charge passed through it, rather than a steady current. It has a long oscillation period and minimal damping. Vibration galvanometers, on the other hand, are tuned to resonate at specific AC frequencies, making them useful for AC bridge measurements. Two critical characteristics define a galvanometer's performance: sensitivity and damping. Current sensitivity refers to the deflection produced per unit current. A highly sensitive galvanometer can detect extremely small currents, often in the microampere or nanoampere range. Damping refers to the forces that oppose the coil's motion, bringing it to rest quickly without excessive oscillation. Critical damping is ideal, allowing the pointer to settle rapidly at its final reading without overshooting. This is often achieved through electromagnetic damping, where induced currents in the coil create opposing magnetic fields. The galvanometer's fundamental ability to detect and measure current makes it incredibly versatile. By adding a low-resistance shunt in parallel, a galvanometer can be converted into an ammeter, capable of measuring much larger currents. The shunt diverts most of the current, protecting the sensitive coil. Similarly, by adding a high-resistance multiplier in series, a galvanometer transforms into a voltmeter. The series resistor limits the current flowing through the galvanometer, allowing it to measure potential difference across a circuit component without drawing significant current itself. Galvanometers find applications far beyond simple current and voltage measurement. They are integral components in Wheatstone bridges and other bridge circuits, used for precise resistance, capacitance, and inductance measurements. Their high sensitivity makes them ideal for detecting null points in these balanced circuits. In medical fields, specialized galvanometers were historically used in electrocardiographs to record the heart's electrical activity. Industrial applications include monitoring and control systems where precise current detection is paramount. Even in some older audio equipment, galvanometers were used as level meters. Despite their ingenuity, galvanometers have limitations. They are generally delicate instruments, susceptible to mechanical shock and external magnetic fields. Their moving parts can wear out, and their accuracy can be affected by temperature changes. They are also typically designed for DC measurements, or low-frequency AC and specialized versions. The advent of digital electronics has largely superseded traditional galvanometers for many applications. Digital multimeters offer higher accuracy, greater robustness, and broader measurement ranges without the need for delicate moving parts. They are also less susceptible to external interference. Yet the principles embodied by the galvanometer remain fundamental. The interaction between current and magnetic fields is a cornerstone of electromagnetism, driving everything from electric motors to magnetic resonance imaging. Understanding the galvanometer provides a tangible link to these core physics concepts. From the earliest experiments to modern precision instruments, the galvanometer has been a silent yet powerful witness to the invisible dance of electrons. It reminds us that even the most complex phenomena can be understood and measured through elegant, fundamental physical principles.